All right. Can you guys hear me? Okay, awesome. Welcome, everyone. Thank you for braving the cloudy weather. I know that's not always great for turnout, but it's still a good turnout. This is our final event of the year, but we have a whole host of additional events coming up for the next 6 months. The first of which, there was a flyer outside there's a lunar eclipse next month that basically happens at the time that we would normally be having the lecture. Unfortunately, it's a Sunday instead of a Friday, but we're still going to do it anyway. So our next event is there's going to be a lecture given by a postdoc here who works on LIGO on gravitational wave astronomy, and then afterwards we'll go out and view the lunar eclipse that's going on with our normal stargazing out on the field, as well as just like viewing the eclipse. Because it's raise your hand if you've seen a lunar eclipse before. So the moon turns red and all of that. So it'll be fun, but we'll also look at other objects in the sky like the Orion Nebula and the Pleiades and the Andromeda Galaxy and so on and so forth. So it should be good. And if it clears up tonight, we'll probably do that, but I don't anticipate it clearing up tonight, unfortunately. And we also have Astronomy on Tap events, which are in addition to our monthly lecture series that you're at now. We have these Astronomy on Tap events that take place in a bar in Old Town, Pasadena, where we have informal talks given by astronomers here at Caltech or the Carnegie Observatories or JPL or various other institutions, and you can have beers and talk with astronomers and hear about astronomy in a less formal environment, and it's totally free. So I encourage you guys to go to that. Our next one of those is January 28th. But the schedule will be up online shortly. I've assembled the dates but haven't gotten all the speakers. What else? Oh, so just as a schedule of what we're going to do tonight, I'll introduce our speaker in a couple minutes, and then he'll give a talk for about 30 minutes, followed by, rather than having the stargazing outside, we'll set up this table in here, and there will be a number of different graduate students and postdocs to answer any questions you might have about astronomy or physics or space, and that'll go until 9 o'clock. And you don't have to stick around, but you're encouraged to stick around if you have some burning question about the cosmos that you must get an answer to. So, and all of our events are recorded, and they're on our website. You can go there. We're also uploading them to YouTube with subtitles and translations, so that other people who aren't able to attend can watch them and find out about all of our science education. So I think that's it in terms of announcements. So to introduce our speaker, it's me. So I'm Dr. Cameron Hummels. I'm a postdoctoral researcher here. And in addition to my science, which I'll talk a little bit about today, I run the public education events here. So I run these lecture series and the Astronomy on Tap, and we do a few other educational events. But let's see, how do I introduce people? I did my PhD at Columbia University and then did a postdoc at University of Arizona in Tucson, and I've been here for 3 years, and I primarily do galaxy evolution studies. So, and I'm going to talk about that. So please welcome me. Okay, so, yeah, galaxy evolution and formation. This is a movie. This isn't real. This is a simulation that a friend and colleague of mine named Nathan Goldbaum put together on a supercomputer that was run out of Illinois of an evolution of a Milky Way-like galaxy. I'll talk a little bit more about what's going on in this later on. But first, let's start with a very basic question. What do we see when we look up in the sky? Yes, tonight, absolutely. This is a pretty accurate rendition of what we see when we look up in the sky. Or if it's a nice day from Los Angeles, we can't see a whole lot just because of the light pollution in big cities. So when there's a lot of light, some of that light goes up, it scatters off of particulate and molecules in the upper atmosphere and reflects back down, and it increases the surface brightness of the sky so we can't see the faint objects back behind it. But let's pretend that we're not on the Hollywood sign and that we're looking out, let's say 300 years ago, before there was a lot of electric light sources, and you could actually see the night sky. So here's Badwater Basin in Death Valley. When you look up in the night sky, for the first part of this talk is going to be historical. Like, what was the state of astronomy 300 years ago, 200 years ago? So when you look up in the sky, what do you see? Stars. Yes, very good. People see stars. What else do you see? Planets. I heard planets. Good. Okay, so planets tend to be, at least in our solar system, the inner planets tend to be much brighter. They oftentimes, you might confuse them with a star. In fact, Venus is oftentimes referred to as the evening star or the morning star. It just looks like a very bright star. But it doesn't twinkle because it's closer and so on and so forth. But the stars, because they're, the planets, because they're all in our solar system, which is a plane, and we also are in that solar system, we see the other planets trace out a path, like a line on the sky, which is called the ecliptic. And so you see these three planets along that ecliptic. The moon also follows it. But I'm not talking about the planets. So let's move on. So what else do we see? We see the Milky Way. Everybody, raise your hand if you've seen the Milky Way. Oh, wow, that's great. Okay, good. I'm glad to hear that. If you haven't, you're missing out. You should go see the Milky Way, preferably at a nice dark site like Joshua Tree, which is only an hour or two away from here, or Death Valley. So people have been looking at the Milky Way for thousands of years. And it's been known for quite some time that the Milky Way, when you see it for the first time, it may not look this spectacular, but this is essentially a composite image of it across the sky. And so it's a big band of kind of milky light, hence its name. But it's been known for several hundred years that it was actually composed of individual stars. It's not just like an extended kind of cloud. Each region where it's glowing is actually composed of individual stars, which you can see if you look at it through a telescope. So yeah, from 250 years ago, William Herschel, a famous astronomer at the time, mapped this out by looking through his telescope. He didn't have a camera, so he was just drawing illustrations of it. And our understanding of the Milky Way is that it's primarily a disk-like structure, with kind of a bulge in the center, kind of like this. And our solar system is about 50% of the way out in that. Now, this is a modern-day image from the Gaia mission that really showcases it. But even a couple of hundred years ago, people understood this. This was actually proposed by the philosopher Immanuel Kant, which is pretty awesome that he just deduced that and figured it out. But So it's been known for a long time, and in fact, we thought of the entirety of the universe a couple of hundred years ago, or even 100 years ago, was composed of our own Milky Way. There was nothing really beyond the Milky Way. That was the universe. So what else do we see when we look up in the night sky? We see comets, right? Comets are icy objects from the outer parts of the solar system, which on their way into the inner solar system start to heat up and start to melt and evaporate that ice off in these tails that are directed back away from the sun. And in fact, a couple hundred years ago, you could get pretty famous by being the first person to discover a comet. In fact, not even a couple hundred years ago. You can still be famous. If you're the first person to identify a comet, then you get to name it, which is pretty cool, right? But when you first discover a comet, it's not usually this bright, or everyone would see it in the sky and say, that's my comet, I'm calling it after, Cameron or John or Jill. And so this gentleman named Charles Messier, Frenchman, he essentially looked to identify comets. And a comet discoverer. And so, but when you first see a comet, when it hasn't yet been identified, it's only a faint kind of extended smudge on the sky. It's very hard to make out. But there are also other things that are faint extended smudges on the sky that aren't comets at all. Feel free to come in. There's still some room in this vicinity. Or you're free to hang out back there too. And there's room on the other side. So there were a number of other things that weren't comets that were faint, extended smudges on the sky, and he didn't want to confuse those with the actual comets, so he identified a bunch of them, about 100 or so objects, and it just so turns out that these objects are actually amongst the most beautiful objects that you can view easily with telescopes. So this is just a smattering of them. They're called the Messier objects. Of course, that was the thing that he got famous for, not naming the comets, but naming the things that weren't comets. And you can see a number of different things. You can see kind of clusters of stars here. You can see kind of cloud-like structures, and so on and so forth. So, as I said, this is the Pleiades cluster. It's a cluster of stars. This was one of the objects. This is Messier Object 45, and we would be looking at this tonight if it weren't cloudy, unfortunately. But you also find other objects like this. So these are referred to as nebulae, which just means cloud in Latin. And it's like a big cloud. This is, in fact, a cloud that's expanding off the surface of a star. It's called a planetary nebula. It wasn't really understood that that was what was going on when it was first discovered. But in addition to these kind of cloud-like things and obviously star-like things, there were also these things, which were called spiral nebulae. And this was the Great Andromeda Nebula. And you can see that it kind of looks cloudy, but it's also kind of spirally. And really the question is, what's the nature of these things? Are they in fact small and really close and basically associated with a star or a handful of stars? Or are these in fact like our own Milky Way? They were referred to as, are these island universes like our own Milky Way galaxy is? And it wasn't really understood what the nature of these things were. And in fact, it eluded people for quite some time. So in 1920, only 100 years ago, we still didn't know what the heck these things were. We essentially, there was something called the Great Debate, where the leading proponents of the two theories got together and argued about, based on the scientific evidence, what they thought these things were. Were they small objects like stars or clouds around stars and really nearby, or were they much like our own Milky Way and very, very distant objects, but very, very large, much larger than we thought things could be? Because remember, we think the entire universe is basically our own Milky Way at that time. But the real way to check is to determine the distance to these objects. If they're nearby, then they're small, and if they're far away, then they're very large. So typically, the way we determine distances in astronomy is much like we determine distances with our eyes. And that is to say, using something called the parallax method. So I want everybody I'm going to conduct an experiment. So everybody, please raise your hand and put an index finger, not middle finger, unless you're really upset with me. And then I want you to alternate one eye open and then switch which eye is open and kind of wink, 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 wink between the two eyes. And what you'll see is your index finger will appear to change its position relative to the background, relative to, I guess, me or this screen. You'll see it kind of jump back and forth. And that's essentially how we as humans, or as most mammals and reptiles, are able to identify how close, get depth perception, right? Because you can see how much something moves relative to its background because we have two cameras, essentially, that we're looking at. And this is done for astronomers as well. So the Earth is orbiting around the sun. So when we look at a nearby star and we image it at July and then wait 6 months until the Earth is at a different position in its orbit and we image that same star, its position appears to change relative to the background stars, much like our index finger appeared to change its position relative to the background. And so you can do this to identify, that gives you, with a little bit of trigonometry, it gives you the distance away that object actually is from us, which is great, right? But the problem is that doesn't work very well the farther and farther the object is. So for instance, if you do your camera 1 and camera 2 thing with my index finger this far away, you probably don't see it move that much relative to the background as you did when it was really close to your face, because it only shifts very, very small amounts of angular distance. And this was the problem when you were trying to measure distant objects with parallax. You just can't do it very well. Fortunately, there was an astronomer at the Harvard Observatory named Henrietta Leavitt who was able to identify another method for determining distance around this period. She basically identified that certain types of stars, called variable stars, would pulsate. And when they would pulsate, they would get brighter for a period and then fainter for a period, on the order of days or weeks. And there appeared to be a relationship between the pulsation period, how long it took to pulse, and how intrinsically bright that star was, essentially giving us, like it told us that this was like a 100-watt light bulb, right? And if you know how intrinsically bright a light bulb is and how bright it appears to your face, you can tell how far away it is. So essentially, this was a method for determining how far away stars were. Just by, you measure their pulsation rate, and then you know how intrinsically bright it is, and then you measure how apparently bright it is, and that gives you the distance. So this was a great method, and there was an astronomer who was here in Pasadena named Edwin Hubble who employed this method. So Edwin Hubble, most of you have probably heard of him because of the telescope and so on and so forth. He did much of his work at the Carnegie observatories, which are like 2 miles from here, and there's still groundbreaking research being done there today by astronomers from around the world. And he did it on the Mount Wilson telescope, which of course is right up the hill, like 6 miles from here. And for a long period of time in the early part of the 20th century, that was the largest telescope in the world. So there's a significant piece of history and scientific research that's been here, part of the Pasadena community for a long period. He's almost always shown smoking a pipe. I don't know why. I guess he was always smoking a pipe. But what he did is he spent a lot of time on that telescope observing objects like the Andromeda Spiral Nebula to determine, is it composed of stars, or is it composed of, like, is it just a cloud surrounding a couple of stars? And what he determined, this is one of his images, he's holding it here, is that not only is the cloud-like structure of this nebula actually composed of many, many small stars, distant stars, much like our Milky Way is, but one of them he identified as a variable star, and he could figure out how far away then this system was from us. And he deduced that it was 2.5 million light years away. And at that point, we thought the Milky Way was on the order of, I mean, we still do, think that the Milky Way is on the order of like 100,000 light years, so it's like 25 times farther away. Which is crazy, right? Basically, everyone freaked out because it meant that the universe was much larger than we had thought by a significant amount. So it really settled the great debate, and it said that these distant spiral nebulae were actually these very large, very distant systems, much like our own Milky Way. And so here's a modern-day image. We no longer refer to these as the Andromeda Nebula or spiral nebulae. They're spiral galaxies, because they're much like our own Milky Way galaxy. This is a beautiful image. So this is what we think of it. And like I said, here's our Milky Way. Here's the solar system, about halfway out in the disk of the Milky Way. And what this essentially did is it increased the size of the universe, what we thought, by about 100,000. So the universe, from our perspective, I mean, nothing real took place in the universe that day, but basically, we realized that it was actually about 100,000 times larger than we had thought up until that point, which blows my mind. Not only did we realize that these distant objects were large and very far away, but they were traveling away from us. So Edwin Hubble's most notable discovery is probably that these objects were traveling away, and the farther the galaxy was from us, the faster it's traveling away from us, which is plotted very nicely here, where you have the distance of a galaxy, and you have the speed at which it's traveling away from us, and you can see all these points. And so the farther something is away, the faster it's traveling away from us, which sounds kind of crazy initially, right? Are we at the center of the universe and everything's just traveling away from us? What he was able to deduce was that in fact, the universe was expanding. Yes, he's awesome. The universe was expanding outward, and so it wasn't so much that we were sitting and everything is traveling away from us, but that space itself is expanding, and so we're traveling away from each other, and everyone appears to be at the center of their own space, and everything's traveling away. And that's why you get a space telescope named after you, is when you do major discoveries like this about the nature of the universe. So very quickly so far, there's a lot of stuff in the sky, including these smudges that we used to refer to as nebulae, but we now call galaxies. These galaxies, the universe is extremely large, and there are many galaxies within it. The universe is actually expanding even more and getting to an even larger size, and Edwin Hubble's really a badass. So, okay, so this is our nearest galactic neighbor, called the Andromeda Galaxy. Again, something we'd see tonight if we had clear skies. This is the version that's on almost every Macintosh desktop. But it's not actually. They've done some photoshopping to it to make it a little prettier, even though it's actually really pretty by itself. So I don't know why they bothered. So what is a galaxy? This is a proposed view of what our own Milky Way looks like if we were looking down on it. Of course, we're not, because we're about right there in the disk. So we can't take a selfie of our own galaxy because it would require a lot of travel for a long period of time, or faster than the speed of light to get up here to take this picture. But this is, based on scientific evidence, this is a pretty accurate portrayal of what our Milky Way would look like if we were to take a picture from it from the outside. It's about 100,000 light years across the disk, and it has on the order of 100 billion stars. And it's made up of stars and gas. It's rotating, but it's actually held together by the force of gravity, much like the force of gravity that holds us onto the surface of the Earth. So we're all familiar with it, right? Everybody has tripped and fallen down. So gravity holds us to the surface of the Earth. It's an attractive force that holds objects that have mass. It attracts them together. So I'm being pulled towards this microphone, and it is being pulled towards me because we both have mass, but it's a very small effect because we don't have that much mass, whereas with the Earth, there's a lot more mass to it, so we're pulled much more substantially to it. But at the same time, we're pulling back on it as well. So in space, if you have two objects, they're being pulled together, and if you have many objects, they're all being pulled together as well. So it tends to pull things together, pull density structures together to even higher density. This was proposed by Isaac Newton. We've had modifications to it with Einstein and general relativity, but the base level is accurate. So thank you, Isaac. So gravity is what's holding us all together, so we can say that this is a gravitationally bound collection of stars and gas. But it turns out that there was significant research done by a famous astronomer in the 60s named Vera Rubin, who passed away recently. And she actually deduced that if you count up the mass from all of the stars and all of the gas in some galaxies, they're actually rotating so fast that they should just spin apart. They should just like fly apart. There's not enough gravitational force from the visible mass to hold it together into one piece. And so that's one of the main reasons that we think that there's dark matter. There's an extra amount of mass that we can't see that is providing the gravitational force to hold the galaxy together from flying apart. There are other pieces of evidence that we have for dark matter, but that's one of the main ones. So I'll add to this list. It's a gravitationally bound collection of stars, gas, and dark matter as well. Okay, so what do we know about galaxies from observations? We've already talked like a little bit about what we know from observations, but when we look up in the sky, many of you may have seen this is the Hubble Ultra Deep Field. This is an image of sky that was imaged for a very long period of time using the Hubble Space Telescope. And you can see a huge diversity in the types of galaxies that you see. Each thing here, for the most part, is a galaxy. You see some red guys here. You see some blue ones. You see some kind of funky shaped ones that are interacting. You see disky structures, like this is kind of disky. There's just a huge diversity in terms of the types and the colors that we see throughout the universe. But the main types are these red ellipticals, because they tend to look like an ellipse, and they're reddish. We're very innovative with our descriptions. I like to think of these in terms of eggs. So I like to think of these as hard-boiled eggs because they don't have a lot of features. It's not red. I guess if it were Easter, maybe this would be appropriate. But so hard-boiled eggs are like the ellipticals, and then you have these blue spirals or disk galaxies like our own Milky Way, which I think of like a fried egg, because you've got that disk component, and then you have like the yolk in the middle. And then, so those are the two main types, but then there's also kind of a third type called the irregular galaxies. These obviously just don't fit well into a category, hence their name, and they tend to be very, very blue. So I like to call them scrambled eggs. But when we fly through the Hubble Ultra Deep Field, because of course the speed of light only is this going to move for me? Do I need to click again? Okay. The speed of light only travels at a finite speed, and so the stuff that's farther away from us, it takes light longer to travel to us. And so this is an animation. We aren't actually able to travel at these speeds through space. As we see stuff from more distant stuff, it's essentially at a younger stage in the universe's evolution. And what we can see from observations is that as you travel through this to more distant stuff, you're essentially looking at the universe when it was younger and looking at these galaxies when they're younger. And you can see that as we go farther back in time, essentially, to more distant objects, they tend to be bluer. They tend to be a bit clumpier. They're different, right? They're different than they are nearby, which is to say, the universe, the galaxies in the universe when it was younger is different than it is today. And we can simply deduce this based on the fact that the speed of light is traveling at a fixed speed. So our conclusions here are there are two major types of galaxies, red and blue spirals, and then there's these irregular ones, which are kind of filling in the gaps. And then galaxy populations change with distance. What else do we know from observations about galaxies? Well, the distribution of galaxies, again, this is a fly-through. We can't actually do this. But the distribution is not just uniform throughout the sky. This is from the Sloan Digital Sky Survey, a major observational effort that took place over the last 10 or 15 years. And you can see that galaxies are distributed in clumps, kind of. There are voids in between them, but you see these kind of filamentary structures. It's oftentimes referred to as the cosmic web, because it's kind of this web-like structure of filaments where you see galaxies and where you don't. And this is a 2D slice through that volume, and you can definitely see these kind of filamentary structures and clumps, which is kind of weird, right? I wouldn't naively expect to find this kind of structure if I just went out and just observed the universe, but this is what we see. So what do we know? Again, a short conclusion case here. What do we know about galaxies from observations? We know that they are groups of stars, gas, and dark matter that are gravitationally bound. We know there are a huge number of them in the universe based on our observations. There's a huge diversity in types, but it's mostly ellipticals and spirals. The population changes as we go farther away, i.e. as the universe ages. And then there's this weird distribution of them in space. But the big question is why, right? Observations are great for identifying, categorizing these galaxies and learning facts about them, but it doesn't necessarily tell us why they are this way or how they evolve. Because for the Milky Way to change in any appreciable amount takes hundreds of millions of years. The Earth, when it orbits around the sun, takes 1 year, right? That's what defines our year. But for the entire solar system to go around the center of the Milky Way, which happens, it takes like 250 million years, which is obviously much longer than I hope to be around or many of my astronomical colleagues. So we can't really study it just by observations alone. Fortunately, we have theory and computers in order to be able to better understand how these things will form and evolve over time. So we can simulate these systems. I'll just take you through a quick scientific method here. What I do is computer modeling of galaxies, like I'm about to show. We represent in a computer kind of a virtual volume, a virtual space, like a chunk of the universe. And then we program, in the case of the simulations that I run there, it's primarily a grid-based case, a grid-based discretization of the volume. And then you program in your dominant physics on whatever scale you're trying to simulate. In the case of the simulations we're going to show here, that's primarily gravity, which we already talked about, and fluid dynamics, just how fluids behave, because much of the universe that isn't dark matter is composed of like gases, essentially. There's very little solid stuff out there, even though you're like, oh, well, I'm surrounded by solid stuff. I'm on a planet, but that's not how most of the universe is. We have to create initial conditions as a starting point for our simulation, because you have to start somewhere. And then we run the simulation forward in time, accelerating time much faster than our experience as humans, in order to go over the millions or billions of years. And then finally you analyze the results and try and compare with the observations that we have of the universe. So we'll do a few different kind of tests. We'll do one with how do we simulate star formation. So for this, we'll start out as our starting point. We understand that stars form in giant gas clouds. The gas clouds are big clouds that are fuel for that star formation. And we'll run it forward. This is a simulation that I'm going to show that was done by one of the graduate students here, Mike Grudich, who's actually giving one of the talks in the next 6 months. So stay tuned. He's a really good speaker and does awesome science. So we start out in a big giant gas cloud. This is about 1 million times the mass of the sun. And what happens is overdensities become more overdense by gravity. Remember, gravity is an attractive force. And eventually you start to form stars in the center, and the stars start pumping out light and radiation, and it blows out the gas that formed them. And then you're left with stars. In many times, these stars tend to be blue because they're very massive stars, and so they're pumping out an enormous amount of radiation. But the Orion Nebula, many of you may have seen the Orion Nebula, is a good example of this in action. So this is a dense cloud where stars are forming and they're blowing out. The trapezium stars, the 4 stars in the center, are these massive stars that are blowing out much of the gas that formed them. And at the end, you're left with blue stars, much like you see in young stellar systems like the Pleiades, which, again, we would see tonight if it were clear. But you're left with stars in clumps, in clouds, or not in clouds, in clumps or clusters from that initial star formation event. So young stellar populations tend to be blue, but as the most massive stars essentially die off and turn into supernovae, you're only left with the redder, cooler stars, lower mass stars. And then those young stars, as they're so energetic and then turn into supernovae, they tend to drive these hot gas winds that blow off. And we'll see some more evidence of that coming up. So enough with just stars. How do we simulate galaxies as a whole? Well, remember our model for our galaxy, the nice fried egg. What if we just take 2 of those fried eggs and we slam them into each other? This is a movie from a simulation that periodically, so it slams these 2 galaxies together and then periodically switches to images from the Hubble Space Telescope of actual galaxies. And what you can see is this very simplistic model has 2 galaxies slamming together, and it's able to reproduce many of the observations that we have of irregular galaxies. Remember the scrambled egg galaxies? When we look up. So these are kind of strange-looking galaxies that are very, very blue galaxies. And they're blue because as these galaxies slam together, they're inducing a lot of young star formation. And those young stars, remember, are very blue stars. I really like this movie. So yeah, we can do a really good job then of reproducing a lot of the observational characteristics of irregular galaxies simply by slamming 2 galaxies together and showing that those irregularities are mostly caused just by interactions between 2 galaxies as they collide. And their colors are also explained by that. But it'd be nice to not start with something quite so artificial as to 2 galaxies that we just set up here and then allow to slam into each other. It'd be nice to start out like in their natural environment in the universe. So let's see galaxies evolving since the beginning of the universe. But for that, we need our initial conditions. We need our starting point to be the early universe. So what did the early universe actually look like? That's a tricky question. But recall that Edwin Hubble's second discovery was all about the expansion of the universe. Now, everything's expanding and traveling away. So if you go back in time, then the universe is smaller, right? And everything's traveling out. And you go back farther in time, and it's smaller still. And if you keep going back in time, well, you get to the Big Bang, when everything was kind of in the same spot and traveling outward. So we can look at distant, light that was emitted shortly after the Big Bang, about 400,000 years after the Big Bang, and that's something called the cosmic microwave background. So this is radiation that's essentially been traveling unimpeded for the last, 13 billion years, and it has a fingerprint of what the early universe looked like. So it's essentially a map of what the universe looked like. Now, for the most part, this is uniform in density. We're only looking at, I think, 1/1000th of a modification relative to a uniform background. But you can see regions of overdensity and regions of underdensity. So if we program that in to our initial conditions for a simulation, we can see how the universe is going to evolve. So this is a large volume of space. It's about 300 million light years across. It's a simulation volume, and as you can see, it's very uniform in its density distribution, but there are very slight overdensities that are programmed from those the observations from the cosmic microwave background. And when we run it forward with gravity on, you can see that very quickly you start to see structure that forms. And essentially what's happening is those very, very slight overdensities are better at attracting the gas around them to them because of gravity, because gravity is an attractive force, right? And it pulls stuff towards them, and it enhances those. And so it turns into this runaway effect. And you end up with this filamentary structure purely due to the gravitational effects. And in fact, this filamentary structure looks a lot like what we saw when we looked at the distribution of galaxies in the universe. It's not uniform in the distribution. It's in this kind of weird cosmic web structure, which is super cool, right? Because we were just able to demonstrate that simulations can totally reproduce the observations just based on gravity and these slight overdensities from the early universe. Finally, we can look at how, again, this is our kind of cosmic web looking at the dark matter on the left, and on the right, this is going to parallel the same rotation, and we're going to see what the gas is doing, not just the dark matter, which is the bulk of the gravitational kind of load. So the gas also falls along these filamentary structures that are defined by where the dark matter is, and in the nodes, in kind of the intersections where these filaments cross, you get a buildup not just of dark matter but also of gas, and in fact that gas starts to get dense and form stars, and you get galaxies at those locations, or many galaxies in some cases. And what's happening, the colors here represent the temperature of the gas, so blue is cool, and then orange and red is hot. So what you can see is as galaxies form, they start having star formation. That star formation, remember, erupts in these hot, energetic winds from supernovae and from young stars that blows out material and causes these explosions over cosmic time. But of course, when we look at the universe, we can't see in dark matter glasses, and it's oftentimes difficult to see with telescopes to see what the gas itself is doing. But we'd also like to, just to keep on this, we can look specifically at a small region within one of those knots to follow the evolution of a single galaxy, not just a huge volume of space that encompasses thousands of galaxies. On the left, we're going to watch a galaxy right in the center here in its projected gas density, and here we're going to look at the temperature of that gas. And what happens is that over time, you see this filamentary structure like we saw before. Galaxies start to fall into our central galaxy. It essentially merges with them. It forms hierarchically by eating its neighbors. And when they fall in, that cool gas, which is red here, falls in, and it causes bursts of star formation, which cause these hot yellow winds to be driven out and blow material away from the galaxy. But really it's forming by just eating its neighbors. So the Milky Way is always referred to as like a cannibal, because it's like, and these simulations were done here at Caltech by one of the professors, Phil Hopkins. But of course, we aren't looking at the galaxies in that gas or the temperature of the gas. We're looking in starlight. When we look at a distant galaxy like the Andromeda Galaxy, we're looking at its starlight. And so this is what that exact galaxy we were just looking at just in the last movie, this is what it looks like as it evolves just from the light from its stars alone. So you can see there are blue patches from the young massive stars, but you can also see red and brown sections. That's dust that forms, and it blocks the light from stars behind it. Much like if you were to stand in a dust cloud in the Mojave Desert, the sun would appear much redder or darker because the dust is absorbing some of that light and scattering the blue light. But this always gives me a little vertigo here. But this is much what a galaxy, I mean, we just watched this galaxy evolve over 13 billion years. Maybe this is only about 12 billion years or 10 billion years, but a significant period of time, much longer than I hope to live. And you can really see a lot of the structure that we see when we look at still frames of actual observed galaxies. So these are snapshots of that, not just that galaxy, but other simulated galaxies that the fire simulations have done. And then these are actual observations of galaxies when we look up in the sky. And obviously the colors weren't spot on, but in terms of the general structure, we're generally reproducing a lot of similarities between the types and the colors that you see in observations and in simulations. And it's, I don't want to go too much longer here, but it's not like we're observing, so. What about the future of our own galaxy, the Milky Way? So our own galaxy is here, and we've got time running in billions of years. But our galaxy isn't alone. We've already talked about the Andromeda. First it was the Andromeda Nebula, but now we refer to it as the Andromeda Galaxy. It's kind of hanging out over here. And there's also the Triangulum Galaxy that's part of it's called the local group. Now, over time, over billions of years, these systems are going to merge. And in fact, the Milky Way and Andromeda will merge to form Milk-Omeda because that's fun to say. But initially, we're both kind of bluish systems because we have active star formation. But as these systems merge, they blow out a lot of the gas that's responsible for active star formation, and they quench. They stop forming stars. And so what you're left with is a more red elliptical population. So this is Milk-Omeda will be a red elliptical as opposed to Andromeda and the Milky Way, which are both blue, kind of disky systems. But they made a nice time lapse of what the view from Earth would be over the next 8 billion years. So here you have the Milky Way and you have Andromeda hanging out up there. And then a billion years later, Andromeda is like much closer. And then it's really, really close. And then it's like, everything's going crazy. And then you're left with just like Milk-Omeda. So you look up in the sky and you just see this kind of like reddish haze instead of the nice disk structure of the Milky Way. But don't worry, the sun will have eaten the Earth by then. So, but this is, don't sell your real estate. That's like 5 billion years away. So, what do we know about galaxies from simulations? Simulations can reproduce a lot of the characteristics that we see in observations. For stars, for how galaxies form by eating their neighbors, and a variety of different characteristics. And then for the last thing that I wanted to talk about, these simulations are not in fact run on like an Apple IIe. They are run on supercomputers. So I have a clip from the movie The Martian, which you may have seen. So this is the supercomputer that actually exists. It's not just in the movie. It's called the Pleiades NASA supercomputer. And Donald Glover here is a young astrodynamicist who's operating. He's doing some calculations on the supercomputer. Oh, his calculations are correct. Oh, that's great. And he's very excited. So there are some things that are accurate about this, some things that are not accurate about this. So computers like this do exist. This is a similar one to Pleiades. This is called the Blue Water Supercomputer. It's in Illinois. It's run by the National Science Foundation. And it does consist of these long rows of many, many, many different computers in a rack. So I think Blue Waters is on the order of 200,000 processors all operating in tandem. Fortunately, you don't have to go there to use it. You can use the internet to connect your computer to it, or it'd be very expensive and have a lot more carbon footprint if I had to go to Blue Waters in Illinois every time I wanted to use it. The room is kept very cool, not so cold that you can see your breath, but it's very cool because you don't want the computers to overheat. At the end of your calculations, it does not tell you that they're correct, but that's okay. So the general conclusions, galaxies are awesome. Observations of galaxies have revealed all kinds of stuff, that the universe is full of them, and they've been around for a long period of time. Simulations can reproduce many of those characteristics, which is super exciting. And don't sell your real estate, but we're going to merge with our neighbor and form something cool called the Milk-Omeda Galaxy pretty soon. If you have more questions, I have some of those movies on my website, and if you want to get involved more with galaxy research studies, there's something called, or even non-galaxy research studies, there's something called the Zooniverse. It's for citizen science. You can go there and start identifying different galactic types, and it gets used in actual scientific research. There's just too many for us to actually do, and computers and AI aren't very good at identifying different galactic types, so we have to rely on humans. So if you want to help out, that's one way to help out, but there's lots of different tasks that you can help out with active research projects. So thank you very much. So do you guys have any? I'll take a few questions and then we'll adjourn for the panel Q&A. Yeah. Okay. Huh. So the question was about the discovery of galaxies that seem to have a ring or a couple of rings around the center of the galaxy. These are called ring galaxies, unsurprisingly. And we don't have a conclusive way to form these. Computer simulations try for a variety of things. There are different ways. One is to have, if you have a large disk galaxy and you like kind of send another small structure through it, it can cause kind of like if you drop a stone into a pond and it causes ripples of material to go outward. It's that sort of thing. But we don't, yeah, it's unusual, and we don't have a really good explanation for these sorts of things. So the question is the grid simulation based on mathematical theory? Yes. So the way we represent hydrodynamics, which is to say how gases and how much of the universe is in fluid form and interacts with each other, we typically represent it either on a grid-based structure called Eulerian hydrodynamics, which is all math. I didn't want to get too detailed into the math here. Or in a Lagrangian representative where it's all made up of particles that represent larger fluid elements. But yeah, it's all math. This is all math. I just didn't include equations because most of the time public talks get really boring. Yes, so the question is, do we use the many-body problem? We absolutely do. For the bulk of the gravitational calculations that we do in this, there's some component of the n-body problem, which is to say, initially when I talked about gravity, I had 4 particles that were each pulling towards each other. That's almost always done in some way representing this many-body or n-body problem, where you have many different particle masses that are being pulled towards each other, and you're calculating the attraction, the gravitational attraction through mathematical formula based on Newton's gravitational stuff that we talked about too. Yeah, sure. The question is, how do we incorporate dark matter and dark energy into the simulation since it's still active and we don't really understand it? So, very good question. Dark matter, so it's true, we don't really understand what the nature of dark matter is, but we do have a really good understanding of how to parameterize how it behaves. Yes, I can't hold in my hand like this is dark matter, but I know how it behaves really, really well on large scales. We treat it like a collisionless fluid. We use usually n-body representation of it, where we have it as represented as small infinitesimal particles consisting of a very large portion of mass. And that seems to do a good job of representing it for the simulations, even though I can't conclusively say like what that matter is. I can say how it behaves. Well, usually, so the follow-up is, would we show how we designed the dark matter how we parameterize the dark matter to someone who's an expert on astroparticle, dark matter, particle physics? Usually not. We're both, like the observations of how these behave, we're definitely, like we read their literature and they read our literature, but how dark matter behaves shows up in a number of observational consequences that dictate what they should be looking at, and they dictate what we should be parameterizing in our simulations. So it's really trying to hit it from several different directions to resolve this problem. Yeah. When galaxies merge, are there collisions between stars? So for the most part, no. So when galaxies merge, actually, we have our galaxy that's like the disk of the Milky Way galaxy is about 100,000 light years across, right? And there are 100 billion stars in it, which is a crazy large number. But actually, most of the space within it is just open space. That's why it's taken, why the nearest star to us is 3 light years away. And there's no stars that are closer. 3 light years is like, from our perspective, is a really long ways away, right? So it turns out that if you take 2 galaxies and you merge them together, it's very unlikely that you'll actually have 2 stars hit each other or 2 planets hit each other. They'll just kind of go and pass through each other. The one thing that won't go and pass through is gas. Because if you take a gas cloud and slam it into another gas cloud, it's not like fitting between, it's not like a sieve or something like that. They'll actually hit and they'll slam together and they'll probably start a bunch of additional star formation. It'll cause shocks in the gas and overdensities that'll trigger a bunch of star formation. So while we don't have to worry when the Milky Way hits Andromeda that like the Earth is going to go hurtling into another planet, what we do have to, well, aside from the other problem that the Earth will be consumed by the sun at that point, but the problem that we have to worry about is that those slamming together will cause a bunch of star formation, and that star formation will cause a bunch of young supernovae, and the supernovae will be bad news for us because it'll cause these big explosions of gas and whatnot nearby. If a nearby star were to go supernova, it would not be great for us. It'd be like a big piece of dynamite going off at your next door neighbor's house. Like, wouldn't be so great. But in terms of actual collisions, it's very unlikely. Yeah. Milkomeda, yeah. So the question is, are there any virtual reality representations of these simulations or of how it would, to see like the Milky Way and Andromeda merging? And to my knowledge, no. But there is a lot of active development in visualization of scientific data sets like these, done by people here and done by people at various different supercomputing centers around the country. So I'll put it on our list. We'll try and do it. I could probably I don't want to keep everybody here, so I'll take 2 more questions, and then we'll pause. And has anyone come in recently? I'm assuming it's still cloudy, right, Yukwang? Okay, it's cloudy. All right. But we'll set up for the Q&A panel. But I'll take 2 more questions and then kind of adjourn. Oh. So the question is, sorry, so everybody can hear. How much brighter would the night sky be if we were closer to the center of the galaxy than where we are right now? It probably wouldn't be, assuming like getting rid of the moon, since obviously the moon is a major source of light in our night sky. It probably wouldn't be that much brighter if we were near the center of the galaxy, but if we were close to, so we're in one of the spiral arms, kind of, near one of the spiral arms. We could be in a region, like if we were closer to other stars, other than just the sun, it would definitely be brighter. But our nearest star is like 3 light years away, and it's not a particularly bright star. Like Proxima Centauri is just like, it's like a crummy star. Sorry, if there are big Proxima Centauri fans here. But it's not the greatest star. So I would say that you could have a brighter night sky if you were closer to an active region of star formation. But that doesn't necessarily mean that if you go into the center, you're going to be next to one. You just need to be like in a denser region in one of the spiral arms. Because most of the bright light in a spiral galaxy isn't just at the center. It's along those arms where there's active star formation. But that's a good question. And there was a gentleman in the back who had a good question. Why does it take so many supercomputers to make an animation like this? It's not so much to make the animation. The animation, one of the movies that I made here, I ran the animation on my laptop. It's to run the actual simulation that's very intensive, because you're representing many different computational elements, usually fluid elements, to represent how gas is moving across the simulation volume, and you're doing that at a very small scale relative to the large size of your simulation box. So, for instance, these simulations are calculating how on the order of like 1 billion or maybe 10 billion individual fluid elements are all interacting with each other, which is really computationally expensive to do, because this is going back to what the gentleman asked before about the n-body problem. So remember, I showed how gravity operated on 4 different particles. So each of those particles has to figure out what the effect is from each other system, right? So there are 4 particles. I have to go, okay, which way am I going to move? I need to know about your mass and distance from me, how much you're pulling me towards you, how much you're pulling me towards you, and how much you're pulling me towards you. But then when you add, and each of those 4 has to do it. But then, so it's called a big O of n squared problem. It scales with the square of the number of particles. So in that case, it's 4 squared, so it's 16. Okay, no big deal. So we add another particle in, then it goes with, there are 5 particles, so it's square, so it's 25. And each time you add more, you're adding the square of that number of particles. So 10 billion is a large number, but 10 billion squared is a very large number, and it's really hard for our computers to do that. I'm sorry, that was a really long-winded and strange answer, but it's an n squared answer. I was trying to live up to the difficulty of the computation. There are advances being done in things like graphic processing units, like GPUs, that were primarily funded by game development and visualization of graphics for video games, that have helped in some ways to do this. So there's a lot of move towards having our simulations relying on this new hardware that's actually being developed just to make video games cooler. So hopefully that'll aid us, and we won't have to use these $100 million supercomputers to do these simulations. Okay, I've yapped enough.
All right, we're going to start our panel. So I've taken the liberty of writing the things that Cameron does, including supercomputers, galaxy simulations, and ultramarathons. You should ask Cameron how he ran a marathon against horses and people riding horses, and he beat all the people and all the horses. So, resident ultramarathon man. Yeah, so maybe we want to go down the panel and introduce ourselves. So I guess I'll start. My name's Dylan. I'm a third-year grad student, and I work on mostly explosions of various kinds nowadays, although I used to work on galaxies, particularly measuring how fast stars form. And the technique that I use is mostly like radio astronomy. So you can ask me about that if you want.
I'm Rachel. I'm a 5th-year grad student, and I'm working on observations of distant galaxies with large telescopes. And in particular, I look at the gas and dust content of those galaxies and what kind of chemical elements are in the gas and dust in those galaxies. And I'm going to give a talk this term, so you should come to it. Next term, sorry.
I'm Yu Guang, and I'm a 4th-year graduate student working pretty much the same as what Rachel is working on. So that's the reason why there's... Yeah, we're actually scientific siblings. We have the same advisor. And I guess to make it more explicit, I work more on the gas and dust around galaxies instead of inside the galaxies, and I also use big telescopes. So that's it.
You guys know what I do. So are there any questions? Yeah.
I just happen to have one.
Yes.
First, thank you.
Oh, yeah.
Every time I'm going to say thank you.
Yeah.
We never get a chance to do this otherwise.
Yeah.
I have a question about explosions.
Okay.
Yes, that's you, Dylan. Could you describe the differences between novas and supernovas, and between the different types of supernovas?
Okay, so the question was, can I describe the differences between novae and supernovae? And there are many different types of supernovae. So there's a lot of detail that I could go into. But very briefly, a nova, or a classical nova, is basically some runaway fusion that's happening on the surface of a white dwarf. So the white dwarf doesn't actually explode. The star survives a nova. In fact, there are many novae that are known to recur. There's one in Andromeda that goes off like clockwork every year, and it actually went off like a few weeks ago. And so, every time that goes off, you see like some astronomer telegrams being like, "Oh, we found it again. Here's another nova." But a supernova, as opposed to a nova, is one where the entire star actually blows up, and the star is completely gone. There are several different flavors of supernovae. So the one involving white dwarfs is called the Type 1a supernova. Pay no attention to the names. They're really stupid, and they're just historical oddities. But a Type 1a is basically a white dwarf that undergoes some sort of explosive burning in its core. And there's lots and lots of debates, lots and lots of conferences arguing about how exactly this happens. But basically a white dwarf has explosive burning in its core, and the entire thing blows up. And that's Type 1a. They're important because we can use them as standard candles to measure how far away things are. There are Type 1b's, which are actually massive stars that collapse and their cores explode. And they're Type 1b's because these are stars that have lost their hydrogen envelope. So you can think of stars like onions. In the outermost layer of the onion, there's hydrogen. And in the second outermost layer, there's helium. And then, there's like carbon and oxygen and neon and stuff like that. But basically, for some reason, these stars have blown off their outer skin of hydrogen. And when those stars explode, they're called Type 1b's. There's Type 1c's, which have not only lost their hydrogen, but have lost their helium shell as well. And then there's Type 2 supernovae, and there's like a million different kinds of Type 2 supernovae. And I'm not going to bore you with the details, but they're mostly also very massive stars that have collapsed and their cores have exploded. You can ask me more about specific ones if you're interested.
So the one thing, the Type 1a is it isn't necessarily a companion star siphoning off material to the white dwarf, which then causes the explosion. There could be other explanations.
Yeah, so the question was, how exactly does a Type 1a explode? You have a white dwarf, and historically, the picture was that there's a white dwarf and there's a nearby star, and the star is just losing gradually some of its mass. It's spiraling in to the white dwarf, and it's giving the white dwarf more mass, and eventually the white dwarf gets so massive that it can't sustain its own weight, and it just collapses under its own weight, and that's what causes the explosion. It turns out that there are many problems actually with that picture. And it's been understood more and more in the last 5 years or so that the favored method for producing Type 1a's is two white dwarfs that are actually very close to each other, and the details of which get complicated. But one of the popular ones nowadays is something called the 6D model, which is kind of a silly name. It stands for, what was it? Yes.
Degenerate double detonation.
Yes.
Okay. Dynamically driven double degenerate double detonation. Is that right?
Yes.
Yeah. 6D.
Yeah. Very, very quickly, it's like two white dwarfs that are spiraling into each other, and one white dwarf loses a lot of its atmosphere to the other white dwarf, and for some reason, which I'm not an expert in, that causes some explosion on the surface of the white dwarf, and that explosion travels around, sends a shock through the white dwarf, travels around to the opposite pole of the white dwarf, and that creates another shock, and when the two shocks meet inside the white dwarf, that is your core detonation, and that explodes the entire white dwarf. It's controversial. Not everybody believes this theory, but this is one of the popular ones nowadays. So there you go.
Thank you.
Yep. Yeah, more questions? Yes.
So we hear a lot about the possibility of Betelgeuse blowing up. What type of nova would that be?
So the question was, so Betelgeuse is a nearby giant star. I actually forget what kind of star it is.
Red supergiant of some type. Yeah, red supergiant, I think.
A red supergiant. Okay. Yeah. Does anybody know what mass it is? Yugong is Googling on his phone. So what I will say, I don't know exactly what kind of star Betelgeuse is off the top of my head. What I will say is that connecting types of supernova, it's 11.6 solar masses and is a red supergiant. Okay, it's about 100,000 solar luminosities. And approximately 900 solar radii. Cool. Okay. All right. So, anyways, Betelgeuse is.
It's not that far. It's 222 parsecs. How many light years?
600 light years away.
Okay, thanks.
Cool. Okay. So, Betelgeuse is like 11 solar masses and is about at the low mass end of the kinds of stars that will blow up. It's thought that the threshold for stars that will blow up versus stars that die by other means is like 8 solar masses or so. So it's not like one of the monsters like 50 solar masses or something. So it turns out that connecting stars with the actual kinds of supernovae that they blow up with was tricky business. There have only been like a few examples of supernovae where you see the supernova and then you can go back into like historical images and actually identify like what star it came from. Like it has been done, but there's like it's been done like 5 times. My best guess is that it'll just be like some sort of ordinary type 2 supernova. So just like a core collapse supernova of some kind. But I don't know for sure. Yeah.
Actually, it's either happened or it didn't happen. Well, yeah.
Yeah.
The sun could have exploded 7 minutes ago. We wouldn't know.
Yeah. It's very unlikely that the sun's going to explode. Yeah. More questions? Yes.
So in theory, if everything's moving away from each other, wouldn't that create like some sort of gap in the universe because everything is expanding infinitely, right?
Well, it's not that everything's expanding away from each other. Is that the space itself is expanding. So the analogy that I've heard is like if you're baking raisin bread in your oven, so you have raisins in your dough, and then the raisins are moving away from each other because the bread itself is expanding. And so it's actually the space-time that's getting bigger. So you can think of like a grid that you're drawing in your space, and the grid points are expanding. So your galaxies, there's not going to be a gap in between your galaxies because the space-time itself is expanding. But actually, Andromeda and the Milky Way are so close that they will merge despite everything else moving away from each other. So everything's moving away, but certain things are so close they'll get closer together, if that makes any sense. Do you have anything to add to that?
Oh, okay. So just think about expanding as a uniformly expanding space-time. So basically nothing is like stretching apart. It's just like you have your gas and you have your galaxies being more diffuse instead of just stretching out a gap from it. More questions? I saw a hand from somewhere in Africa.
Is our solar system in a relatively clear stretch of space, or are we in a dusty stretch of space?
Well,
You mean the solar system or the galaxy?
If appropriate, is the Milky Way galaxy in a dusty?
dust exists inside galaxies for the most part because it has to be pretty dense to form dust. So, I mean, I don't think the Milky Way is in a dusty area itself because the dust is inside it, but the solar system, would that be in a dusty area? I don't think so.
Bubble of some kind, aren't we?
I think we are. Do you have anything to add, Cameron? Yeah, I don't think we're in a particularly dusty area, but I'm not really sure.
So I don't actually know, but I vaguely recall reading somewhere that we're in like a bubble of some kind, like
Dusty inside or a clear bubble?
clear bubble. Yeah. So maybe like some supernova went off like millions of years ago or something like that, and like cleared out some space, but I don't actually know off the top of my head.
So I work on galactic dust, not inside our galaxy, but in other galaxies. And the dust actually exists mostly in the mid-plane, so not so much up and above or below the galactic plane, because it has to be dense to form dust. We don't know how it forms, but it could be even in supernova explosions. So you find them more in, kind of crowded areas, which is why when you look up at the sky, you see the dust kind of like along the plane of the Milky Way, if that makes any sense. And there's more of it towards the center of the Milky Way, because you're seeing a larger column of dust towards you. But yeah. Any other questions? Yeah.
So there are ways to know it. So first thing is that you can compare the colors. So basically galaxies have their particular color that's different from stars. So in a color diagram, you can actually pick out some kind of the galaxy. Well, you can start with red, blue, and green, but astronomers invented other colors with.
If you took a red filter on your camera and then a green one, and then you subtract red from green, that's what astronomers call color. So if you would take one color like red minus green versus green minus blue, not that, but like some sort of analogy to that. We use weird filters, but you can plot it on a graph and show like where the galaxy falls is indicative of what kind of galaxy it is.
No, I guess
that's it. Yeah. Okay.
then you can just observe the spectrum.
Yeah, but you could also directly see whether it's a galaxy compared to a star, for example, because if it's smudgy, right, like a star is so small that like you would never be able to actually see the structure. But if it's a smudge, then it's a galaxy of some kind.
Like a nebula instead of a galaxy.
Oh yeah, sure. It could be a nebula of some kind. Mm-hmm.
But if you have a spectrograph, which you can use to disperse the light into different frequencies, and then you can see how much light you have at each frequency, then that can kind of form a particular shape that is more indicative of a galaxy versus like a nebula or a star, because you have different, your galaxy is a composite of lots of different stars emitting at different wavelengths because they're different brightnesses. And then you have gas in your galaxy, you have dust in your galaxy that emits at certain wavelengths, and all sorts of things. If you have enough of these like spectrographs and you have enough of observations at different frequencies, you can construct kind of what your galaxy looks like over different frequency bands and what is composing it, basically.
So a spectrum of a galaxy would be very distinguishable from the spectrum of an individual star.
Well, it depends on how wide of a wavelength range your spectrum covers. So if it's a very, very wide frequency range, you can definitely tell. Like a galaxy will look a particular way because you have the stars and the UV, and then you have dust emitting in the infrared and the radio wavelengths. But if you just look it up, like a short swath of it, you might only see, composites of stars, or you might look like a cluster or something. I don't know.
That leads to a question.
Yeah.
I read somewhere where they would take a spectrograph of a very distant galaxy and be able to see supernova that had happened in that galaxy. Well, the galaxy is so small to begin with. How can they differentiate when they look at the spectrum that there was a supernova there and not just more light from the galaxy?
Okay, so supernovae look very different from normal. So the question was, sometimes you can point a spectrograph at a distant galaxy. Sometimes that galaxy is really small. So how can you tell the difference between a supernova and a galaxy and just the galaxy itself? And so there are a few ways. So for one, supernovae, especially when they're young, tend to look very, very different from galaxies. Right. And one thing that you can learn from a spectrum is a spectrum has certain what are called lines, right? And those lines are just signatures of different chemical elements. So for example, hydrogen has a very specific line called H alpha, located at 6,563 angstroms. In nanometers, okay, six. Yeah, whatever. I mean, yeah, it's yeah, it's.
If you're looking at your eye, it would be red.
Yeah, it looks red with your eye, as Rachel pointed out. And basically, if you look at a galaxy, you can look at like how wide that H alpha line looks like, right? And that width tells you about like how fast the gas that's emitting, the hydrogen gas that's emitting this H alpha line is traveling, right? So typically for like a star formation region, you might see the gas traveling at like 50 kilometers per second or something like that. But for a supernova, you would see it traveling at like 10,000 kilometers per second. And so that line would just be like a mountain, and you would see like all sorts of ripples in your spectrum.
So the supernova has, because of the explosion, has this
Yes.
moving at a very, very high speed.
Yeah, exactly.
At that speed,
Mhm.
that's how you can tell the difference.
Yep.
Your spectrum would evolve over time. So if you pointed your spectrograph at it at a different period in time, it would look different than when you first discovered the supernova. So if you point it back again a few days later, a few weeks, months later, it would look completely different.
The supernova is so bright that it competes with, it's comparable to the output of the whole galaxy. Well, it's bright.
Yeah, there have been supernovae in nearby galaxies that you can actually point your amateur telescope at and see them. My dad is an amateur astronomer, and he's looked at supernovae I think a few times with his telescope. Maybe he's just wanted to, but he hasn't been able to. But he's sent me text messages about this. So I think you actually can see them if you look at the right nearby galaxy. If you have a big enough telescope in your backyard, you can do this. But yeah.
How long does a supernova last? Is it like a bell curve with the energy that's coming off?
Yeah, so the question is, how long does a supernova last? That depends very strongly on the supernova, and it depends very strongly on what wavelength you're looking at. So there are certain supernovae that last only for a very short amount of time. So there is a famous explosion very recently called AT 2018 Cow. I just like the name. So, the first supernova to be discovered in a year is just A. The next one is B, right? And then when you get to Z, then you start with like AA and AB and stuff like that. And so now we're finding tons of them, and we're getting to like COW now. And it happened to be a particularly interesting one and happened to have a particularly interesting name. That one actually rose extremely rapidly. It brightened by almost like a factor of 100 within like a day or two. And it faded, I think, like over the span of like a week or two or something like that. There are other supernovae. This is one of the alphabet soup supernovae called type 2Ps that sort of brighten up, and then the P stands for plateau. They just flatten out for like months, and then they fade away. So this is like the traditional way of looking at supernovae, which is using visible light, kind of light that your eyes can see. You can look at supernovae in the infrared, and we have a friend named Jake who does this. He's a grad student here, and they can last for years in the infrared. I work in the radio. I actually read a paper very recently that was talking about like observations done in like the 2000s of a supernova. I think it was 1957D, and it was like 50 years later or something like that, and you could still see it in the radio. So it depends very strongly. Anything from like days to like decades. Mm-hmm.
The longer the wavelength, the longer the period you can observe.
Usually, yeah. Mm-hmm. Mm-hmm. Yeah, the longer the wavelength, the longer the period you can observe it for, usually. Yeah.
But I guess, the explosion happens, and it's very violent, and all these things that last longer than kind of wavelengths, it's kind of like the burning afterwards.
Mm-hmm.
The explosion itself, it's probably kind of fast.
Mm-hmm.
How fast is the explosion itself?
Yeah, so the explosion itself, it depends on what you define as the explosion, but it doesn't last for very long. So what happens, let's say we have a massive star that collapses, and its core starts to explode. Well, what's happening when the core is exploding is that the rest of the star is still collapsing. It doesn't know about the explosion yet. And so the explosion starts to like rip through the rest of the star. And you have this shock wave that's like going through the entire star. You can't see the supernova yet. None of the light is able to escape because the light is just trapped inside the star. But when it reaches the surface, you have something called the shock breakout. This has actually been observed, I believe, twice. Once was just the super, super lucky amateur astronomer who was like taking a picture of this galaxy and like was like, wow, there's like a bright thing that just appeared like over the course of the night when I was looking at this galaxy. And it turns out that that was a shock breakout. And it was like one of the two that have ever been observed or something like that. There are probably more than two. It was just two that I know of. Another one was just something that was also super lucky. An astronomer who was at Caltech, she was a grad student here, Alicia Soderberg. She was pointing an X-ray telescope at this galaxy, trying to find like the afterglow of a different explosion, an entirely unrelated explosion. And she happened to find like, you know, a supernova that had just had its shock breakout. And it turns out that shock breakouts are very bright in the X-rays. Okay, anyways, I got on a tangent there. Basically, you can get very lucky. But after the shock ripples out to the surface of the star, then you can start having gas that's ejected, right? Like the insides, the guts of the star are just being thrown out in the explosion. And so that takes like a few hours or so for that to happen. And then afterwards, the stuff is just expanding, right? And it's cooling, and there's like radioactive decay that's happening in it that actually powers a lot of the light that you see in a supernova. And all sorts of things happen. And those are sort of the embers that are that you were referring to that are just cooling. Mm-hmm. Yeah.
Is there any sort of direct correlation between the ones that sort of go out quickly and the ones that plateau versus the amount of energy behind them versus strikingly very?
So the question was, is there any relationship between the amount of energy in an explosion and how fast it changes? I should know the answer to this question. I think it's a little bit complicated in that like there are many different energy sources in a supernova. So I mentioned briefly that radioactive decay is important. So in particular, it's nickel 56 decaying into iron 56 that produces a lot of the light that you see. And the plateau is just due to a lot of this nickel decay. And that tends to have about like 10 to the 51 ergs. Ergs are just a unit of energy that astronomers use that nobody else uses. They're like very, very violent explosions that may have like 10 to the 52 ergs, like 10 times more, called gamma ray bursts that are associated with like certain types of supernovae. But and those are actually very fast. So tentatively, yes. The shorter the explosion, maybe the more energy. But I think there are lots of exceptions to that. Mm-hmm. Yeah.
About our own galaxy, how do we know the shape of our own galaxy? We don't really have a snapshot of it. We kind of assume that it's like the Andromeda galaxy, but how do we know that? So how do we know the shape of our own galaxy?
Yeah, so the question is, how do we know that without being observing from outside, how do we know the shape of the galaxy from inside? That's actually a very good question. Astronomers have been struggling for a long while to actually know what the shape of our own galaxy is. So for a long time, people actually just thought that our own Milky Way galaxy is actually just the twin of the M31, the Andromeda galaxy you just mentioned. So in a lot of old diagrams, you see that people were just drawing the Milky Way galaxy exactly the same as the Andromeda galaxy, but that turns out exactly. That's right. But as time evolves, as astronomers did a lot of more observations, people start to realize that that's not the case. How did astronomers know that? It's basically just to see the stars, just to count the stars around us, and to count the densities, to count the distance, and then you will figure out how the 3D distribution of those stars are, at least around our solar system. So more recently, astronomers have launched a satellite called Gaia, which is actually extremely good at counting stars. So this satellite, this telescope, has been observing for like 3 years, maybe, and with its very high precision of measuring where the stars are, as Cameron mentioned in the lecture, you can actually figure out with the parallax, figure out the angle difference while the Earth is orbiting the sun, so you can actually measure very accurately where how far the star is. So by doing that, we actually have a very good sense of how the Milky Way is right now, thanks to that satellite.
And you can also measure the distribution of the dense gas in the Milky Way by looking at electronic transitions of hydrogen. When it's very cold, the state of the atom kind of flips up and down, and you can see that and actually measure where the cold gas is in the galaxy. Make maps of that.
Yes.
Okay, from a human perspective, if I want to take an overhead shot of the Milky Way, how far away would I have to be from the Milky Way? The second part of the question is it possible to have gases and dust in such density that it would block out my view as I'm observing the Milky Way?
I will answer the first part, and I'll let Rachel answer the second part. So the first part is how far do we need to go before we can actually take a headshot, like a selfie, a selfie of the Milky Way? Well, the radius of the Milky Way, let's just say the disk, is approximately 10 kiloparsecs, 30,000 light years. So you need to go approximately that far above perpendicular to the plane to actually see the disk.
And then as to whether there's dense gas or dust blocking our view if we were to go out that far, there is gas surrounding the Milky Way, but it's very diffuse gas. I don't think it's nearly as dense as what you would see if you were to look up in the sky and see like dust lanes in the Milky Way. The dust resides in the middle of the plane and the disk of the galaxy, and then there's gas surrounding it, but it's very diffuse, and Dylan's drawing a diagram. So you have the Milky Way is kind of a disk, right? And then there's a bulge at the center, like Cameron drew in his talk, and there's also a diffuse halo of gas surrounding it. And then inside of that, there's like a few stars that are just kind of dispersed around. Do you have anything to add?
Oh, no. I was just going to say the fried egg model, remember?
Yes.
Yeah, no, you'll see more. But as Rachel was saying, so there's the fried egg, which is mostly composed of gas and stars and dust. And then there is more stuff in the larger volume around it. So the gravitational influence of the galaxy extends out about 10 or 20 times farther than that, but there's very little stuff out here. The density of stuff is much lower. So that's why when you look at distant galaxies, you just see the fried egg. You don't see the much larger sphere of stuff that's surrounding it because it's so low density that it's not emitting very much light. That's right. You can see the stuff. We can see out of our galaxy easily. When we look at the Milky Way in the night sky, you see the plane of it across the sky. But if I look out in that direction where I'm not looking in the plane of the Milky Way, I can see very well because there's just not as much stuff in that direction, in the direction off the disk, off the white part of the fried egg, to keep with this ridiculous analogy. Okay, so the question was, if dark matter behaves in a collisionless manner and there's no friction, then why does it lose enough energy to flow into filamentary structures on large scales? That was the question, right? Okay. The main thing is that it's not really frictionless. It is losing energy with time. And that's essentially done, there's something called dynamical friction, which is not friction in the way of what you think of where you rub two structures together, but it has the same effect. Friction is essentially a way of dissipating energy, usually kinetic energy, motion energy, in a different form, usually heat. In the case of dynamical friction, essentially what's happening, it's kind of a weird effect. If you have many, as in our galaxy, if you have many small particles, we'll call them stars, but they could also be dark matter particles, and you send a more massive structure through that kind of sea of these particles, its gravitational influence is going to attract things towards it. But if it's moved a substantial distance in the time that those things are traveling towards it, it'll build up kind of a wake behind it, an overdensity of structure behind it. That stuff is more massive than the stuff in front of it, so it's pulling it backwards. So it's losing energy as it's flowing through this sea of material. That energy is going into the buildup of structures behind it. But effectively, this is a way that you can get, when galaxies merge, if they were totally frictionless, then they just turn into orbits. But they slowly lose energy and collide and coalesce into a single structure. So that's essentially to just answer how you can have an effective friction even without having things rubbing together, a loss of energy in this form. But yeah, that's one way that you can effectively get structures to form out of a relatively uniform background instead of it just flying all the way through. It dissipates large scale motions in this way. Yeah, it's like a turbulence kind of thing. It's a cascade of motions from large scale down to smaller scale. There is some loss of energy from gravitational waves, but not usually on that kind of scale. So the question was, if we're not sure at which time baryonic matter, like protons and electrons, formed versus when dark matter formed, how can we have some sort of chronology to how the simulation proceeds to mimic reality? The dark matter or the baryonic matter is forming at a very, very short period after the birth of the universe. We're talking like less than a second. And so, whereas these simulations, I showed the cosmic microwave background, that's usually what we're using as our initial conditions for the simulations, and that's about like 400,000 years after the birth of the universe, after the Big Bang. So at that point, the dark matter is fully manifested and the baryonic matter is fully manifested, and they've been hanging out together, doing their thing for like a few 100,000 years. So it's not really a problem. If we were to try and go back beyond, to very, very early periods, like less than a second, this would be a problem, but we don't dare go back that far because we don't really have, it's all theoretical construct of what's going on at that period. We don't have a lot of observations from that era. Absolutely. Oh, great question. There's a whole committee that. So the question was, who gets to tell the Hubble Space Telescope where to point? Is that basically the question? And do we ever have any say in where it points? Yeah. So scientists and even non-scientists could potentially propose. Essentially, it's run by NASA, and as many space telescopes are, and it's paid for with public funds, taxpayer funds, and so it's a resource that any American can write a scientific proposal and say, I want to do this science project, and in order to do it effectively, I need the Hubble Space Telescope to point at that object over there for an hour or 20 hours or something like that. And if you do that, then that should give me the data that I need to solve this important question about the origins of the universe or how stars evolve or something like that. And then lots of people submit these sorts of things, usually from academic institutions like Caltech. And then there's a committee that's made up of people from the scientific community, but not the ones who are submitting. So they're not like, oh yeah, I'll accept my proposal. You know, there's no political aspects there. And I've sat on one of these committees, and you go through and you read all of these proposals. They're usually like 10-page long proposals, and you read them through and you're like, oh, this is pretty good. Oh, this isn't pretty good. And you decide you only have so much time that you can allocate for that next year. You decide whose project is the most interesting and the most efficient. Like maybe this one's really cool, but it needs like 10,000 hours of observing, whereas there are many better ones that there are other good ones that need a fraction of that period. And so then you rate them and say this one is good or this one is bad. And then there's some program officers at NASA who decide ultimately who gets the time and who gets the money. But I just proposed, not for observing time on Hubble, because I mostly do theoretical work. So I proposed to get money to support the work that I'm doing that's mostly used for the interpretation of observations from Hubble. But it goes to similar panels. So that's how it goes. Do you guys want to add anything?
I'll add that Hubble has a cool Twitter account where you can it'll tweet where it's pointing at any given moment. It's amazing if you want to log on. And it'll tell you like which astronomer requested to be pointed at this direction. It's kind of cool. And a lot of large telescopes are actually allocated time this way, like we proposed for the Keck telescopes in Hawaii in a similar manner, which is a certain number of institutions that kind of combine together to form that get time on this telescope. And so.
And that's also how the supercomputers that we use also allocate time on the computers via this method. You propose to do a cool project because they only have so many resources. And again, the supercomputers that we usually run on are either run by NASA or the National Science Foundation or the Department of Energy. And so you propose and say, I want to use the computer to do this project. And they're like, okay, here you go. And then you can run it on the supercomputer for however long you need. But yeah, it's just a democratic way of doling out a shared resource to, a subset of all the people who apply.
Suppose there's an event, say a supernova, that you need to examine now. Can astronomers kind of like put in an emergency request?
Yes. Yes, definitely. Do you want to talk about?
Yeah, so I've never actually done it myself, but I've had it. Oh, sorry. Suppose that there's some sort of very fast evolving event that happened, and you need data now. Otherwise, your supernova is going to disappear or something like that. Can you put in an emergency proposal into some telescope and get time? And the answer is yes. I've never actually done it myself on super short time scales, but I've had it happen to me. So I was observing, I was in Hawaii actually, observing on the Keck telescopes where this is like a week after perhaps one of the most important explosions of the decade. The first neutron star merger happened. And what happened was I got a phone call from Mansi Kasliwal, who was one of the professors here, and she was like, I'm sorry, I'm taking the first hour of your night because we're going to start, we're going to observe this neutron star merger. And I was like, okay, cool. This is much cooler than what I would have been using that hour for. So, so the way that this works is that prior to the actual event happening, she actually submitted a proposal saying, if there were such an event to happen, then I'll be able to like interrupt for like 1 hour and get the observation that I need. And so you can do that basically with most telescopes. Target of opportunity, that's what it's called. Yeah. The Hubble, yeah. Same thing. Mm-hmm. Mm-hmm.
In fact, when that happened, Monty Coslewall, the professor that he was alluding to here, the Twitter account that runs the Hubble Space Telescope and says, "Oh, I'm pointing at blah blah blah," because of this professor, it tweeted that it was looking at an object that Monty Coslewall had observed, and it was supposed to be a secret because it hadn't yet. There was an embargo on that news to the scientific community. There were only there were a decent number of people within the community that knew about it, but it wasn't supposed to be tweeted publicly. And so it was kind of like, oh shoot, we need to delete that tweet because it revealed this information about that the Hubble Space Telescope was observing this target of opportunity from this explosion. But yeah, almost all telescopes have this, that if there's a certain set of conditions, like an emergency, we've got to look at that comet that's going to hit the Earth right now or whatever, like everybody's like, okay, let's go, let's switch. There's no battling to the death in the room. No. Yeah. A trip to Hawaii.
Yeah, that's correct. So the question is, what's the benefit of actually going to the site to observe instead of just doing a remote observing? Like, we can actually control the Keck telescope in Hawaii here in one of those remote observing rooms in this building. I guess, so one of the benefits is that you can actually be face-to-face to the support astronomers. So when you're a scientist actually using the telescopes, there are other people doing their job to support you. And so, for example, there's support astronomers in the Keck Observatory who are actually well-trained astronomers who support you in a way that how you can use this instrument to achieve your science goal more efficiently. There are also telescope operators who actually help you to point to the target. I guess the benefit is that you can actually have a face-to-face exchange with them. And why it's important is that, for example, when this is a new instrument, like Keck had a new instrument a year ago or 2 years ago, I can't remember. And after its commission, we are actually one of the first people to use that instrument. And we don't know a lot of the instrument, how to use it, and like how to correctly, more efficiently to point our telescope, to point our instrument to observe the targets we want to observe. That will be the chance that going to Hawaii to observe on-site being very beneficial.
Can I add something? And there are a lot of telescopes, and Keck is not one of these, but there are a lot of telescopes that are in more remote locations that you actually you don't have a good enough internet connection to do remote observing, so you have to, like the ones in Chile, you have to go there because the internet is not good enough to do it remotely from here in California.
Yeah, and one other thing is sometimes, especially when you have several nights in a row, it's nice to just like be on site and not have distractions. So I was talking about this with Evan Kirby, who's another professor here, and he has this like adorable little like 5-month-old puppy or something like that at home, and named Panda. She's the cutest puppy, except she is like so hyper. She will like, endlessly lick your nostrils, and this is like really nice during the day, right? But you don't want that after like you've stayed up all night and you're just trying to sleep. I mean, this is actually the reason he's cited for like why he goes to Hawaii. I mean, there's also like a really nice facility just for sleeping, like at the observatory. So after you've stayed up all night, you really don't want like the sunlight interfering with your sleep. And so they have these hardcore shades. Like they're actually like wooden. You close